All right, guys, we're going to kick off our next presentation. Next up, we have Saranchak, who's going to talk about privacy vulnerabilities and mitigation techniques in machine learning.
Great, thank you. I'm Saranchak, and I am a applied research mathematician with CTC here in Johnstown. And happy to be here. I'm glad to chat with you today about a really exciting field within security and privacy. Within that field, it's sort of, I feel like there's a lot of energy around within security and privacy, and everything's sort of changing day by day. And this is certainly one example of that, where this is a very active research field within the community right now. Very young, but very active and small but growing. So I'm happy to kind of talk about these topics with you today, convey some of the work that our team at CTC has done along this avenue. And within the greater environment as well, machine learning, that's a relatively sort of new and younger field as well. So it's exciting to be part of one that's within a field that's even young itself. So what I hope to, what I'm going to talk with you about today is just sort of take a moment to kind of level set, talk about machine learning, talk about the current state of machine learning, how we got there. Then once we have an idea of that, talk about some of the vulnerabilities in relation to privacy and security that exist within machine learning. And then from there, I'll give you, drill down into one example, known as the membership inference attack, and one possible mitigation technique against that attack, called differentially private stochastic gradient descent. Okay, so let me just take a couple minutes to level set here. The last decade for machine learning has been very energetic, very exciting. There's a lot of focus, a lot of energy in the field right now. A good part of that comes from three external forces. I'll mention two from here, and then I'll bring in the third one a little bit later. The first one of those forces is the tremendous amount of advancements that have occurred in infrastructure, in particular distributed infrastructure, GPUs, that have taken place at places like Amazon and Google. Seeing this occur and evolve over the last 10 years has been just really rewarding, really exciting. It's to the point now where anyone that has a machine learning problem or analysis problem in general can go online and buy some infrastructure at a relatively cheap cost. They can upload some data, they can make a model that is highly accurate, and they can make extremely accurate predictions that they then roll into their own application. Normally, or a lot of the time, the use cases for these are your iPhone. So they want to make some sort of machine learning model that they can deploy onto your iPhone. And that gets into the second sort of unique factor that is behind this large expanse of machine learning, and that's data. So when they have their model on, or the application on your phone or on a mobile device, they're able to collect this very unique data that they're trying to discover causation and correlation to behaviors or other things like this with the model. And so with that data, it's large scale, it's diverse, and that's been able to make the models even more accurate within the last number of years. And in particular, one field of that is deep neural networks. In particular, those models are extremely accurate and been very successful. So probably about 10 years ago or so, and leading up to that, for companies like Cisco or Google, there was really this idea that the source code was very unique and proprietary, and that's where the secret sauce existed. That started changing in a large way about 10 years ago, like I said, where they no longer considered their code to be their unique IP. It was being stolen, it was being reverse engineered, and they really had to adapt their business model. Well, this fits in nicely with machine learning and the story there in terms of free and open source code as well. Because it's to the point now where, since anyone can fire up these really advanced infrastructure and do it relatively cheaply, that's no longer the differentiating characteristic for business models. It's all about the data. More unique data, that's what it's all about right now. And so it's often said, you might hear that data is the new source code. And that's sort of what's meant by that. Is, differentiating factor, proprietary information is all about the data. And that's what we really want to keep sensitive, or try to keep it from being exposed for many reasons. So that's sort of where we're at in terms of the success of machine learning. But it's all, like I said, it's all about the accuracy. We want these models to be highly accurate. So how do we build these models? What does the model look like? Up here on the left, I want to collect some data. The data that's displayed here is a little bit hard to see, but and it's not displaying exactly correctly, but it consists of 10 rows. So there's 10 rows there. And each row corresponds to an object. So there's a bird up there, there's a plane up there. It's a picture of that object. And I have 10 columns, so that's just 10 examples of that class. And what I want to do is I want to train a machine learning model, a deep neural net, to identify that object class based upon that image. So what I can do is I can take all that data. This is just a small sample of how much data I have. And I pass that through and I train up this machine learning model. Once that's done, and I do it to an accuracy that I feel is good enough for my application, I can deploy that model so that I can use it, others can use it. And how they use it is they want to pass in new data, so that would be the classified part over here, as I move to the right. So I pass in a new image that the model has never seen before. And if I built the model correctly, it should be able to tell me what object class that picture is. So in this case, I pass in a horse, and it should identify on the right-hand side that most likely this object is a horse. That's the whole sort of machine learning pipeline. That's all of it in a nutshell. Within that, within just this pipeline itself, there's a number of vulnerabilities. The first one is that since this model is out there, it's meant to be used. And it's meant to have data come in and put a classification of what that object is on the output. So really, as someone who's using this model, I can pass anything into it that I want. As long as it's of the right sort of format and maybe the right type, I can throw anything in there. So I might put the image of the horse in there, but I might also take that image and just tweak it slightly. And do it in such a way that I can't tell when you look at it, you can't see that there's any difference there. But to the model, it might classify it completely different. And possibly in any way that I want it to. So as I move back, another type of vulnerability there is model stealing. So these models are out there. If I can access them, if I can query them via any API, I can see what it's doing. I know what it's trying to do. And so there's nothing that's going to stop me from making another model that does the same thing, to maybe even a higher accuracy. So it's called model stealing. As I move more to the left, if I have access to, or if an adversary has access to either the data that you're using, or the software, or maybe the infrastructure, they can tweak it in such a way that the model will behave normally when you're looking at it. But during certain circumstances, it'll react completely different in unexpected ways. And they call this model poisoning, or inserting a backdoor into the model. One common one that's out there right now is that with autonomous vehicles that are using these neural networks, they've been trained on stop signs to recognize stop signs. And you can poison that with just a few data-labeled data points, so that when it sees a stop sign with a yellow post-it on it, it'll identify that as a yield sign or whatever else, whatever other kind of sign you want it to recognize, and it won't stop. So that's an obvious public safety concern. Okay. Now, as I move all the way to the left, this is the thing that I'm going to talk about today, the thing I'm most concerned about, is that data that I use to train this model, and this is data that I consider very sensitive and very core to my business unit. There are attacks that can leak some information that will tell you about that training set that I used, or that I spent a lot of money collecting and curating, and potentially it'll give you information about it. These are two attacks are called model inversion and membership inference. So what I'm going to talk about today is membership inference. And the question behind membership inference is an adversary wants to know, be able to determine whether or not this specific piece of data was used to train that model. So it's a fairly simple question. I have a piece of data. Was it used to train that model? Okay. If you have questions at any point, by all means, tell me. So this is just sort of a graphic representation of it. So on the left there, I have an adversary. The model is in the middle there. That's what's deployed. You can access that. On the right-hand side, the adversary wants to get to my data that's sensitive. They can't really necessarily see what it is, but they want to be able to determine what information about it. So the things that they can do is they can obtain some data that they believe might be in my model. Okay, so here's some samples of birds that I might be using. And since the model's out there, they can put those data points through the model and get the outputs from it. And the adversary, what they want to do is just be able to look at that output from the model and be able to say whether or not that data point was there. Okay, so maybe I can determine, just by looking at the output, which one of these data samples were in and which one were not. Okay. Any questions? Yes?
Yeah. So that's not perfect, right? Because in a lot of fluid models we talked about in neural net, they're implement random jitter, like drop out, and things like that, purposely to keep them fitting on my model. So, like, this doesn't really seem super reasonable to me because you really just use the accuracy of the model. I was wondering if you could elaborate on that a little bit.
Sure. So one way to obtain both accuracy and generalizability in terms of machine learning when you're training up, there's a number of techniques that have come out in the last couple of years about how to do that so that your model doesn't overtrain on particular data points. And one of those techniques you mentioned was dropout. Those all kind of help out your accuracy and data augmentation. They help out your accuracy, but they're still part of the model. And it's an open question as to how they impact these attacks. It's one of the things we look at CTC. So it's sort of an open question. This is a very open research field. There's a lot of low-level hanging fruit. And that impact of model design is one of the things that research is looking at now. Okay. But nonetheless, you give me that model, I can still attack it in this way. Okay, so the way that I'm going to attack this model, the way that this membership inference attack works, is sort of the basis of it is the shadow, the model stealing. So I'm going to steal your model, and I'm going to create these other models called shadow models. And they're basically going to behave exactly the way that the target model is going to behave. They have relatively the same accuracy, the same objective. They're looking to classify these objects. And I'm going to create them using some data that I might have that I believe that you've used. Okay, so the private data up there on the top left, I have an idea about what that is, about what you're using, and I want to test out the hypothesis. I can't see your sensitive data perhaps, but I can see your target model. And I can do that model stealing based upon my access to that model. And depending on how much data you have and the accuracy you want to achieve, you can create as many of these shadow models as you want. Okay. With those shadow models, okay, I have data that I've held off to the side. Once I have that model built, I can pass data through it to create, to obtain the output, which are these probabilities. Okay, so I know which data over here was in the training set for each shadow model that I built, because I built it. I also have some additional data on the side that I didn't use for the training. I'm going to call that a test set. This is also sort of a good thing to do in machine learning in general, is to allow a test data set to obtain an idea of how well your model generalizes. So I have my data over here. I can pass it through my shadow models. And what I get on the output is the probabilities. It's a probability vector of what it thinks that class is. Well, for for each one of those that I pass through, I know whether or not it was in the training data set. And so I can add an additional label over here, in and out. In representing it was in the training set, and out meaning it wasn't. So what I have now over here is I have a new data set, completely new data set, where the features are these probabilities, and I want to be able to predict that label in versus out. So this is a common problem in machine learning, a binary class prediction. And in particular, I want to predict in or out, and I want to create a machine learning model to be able to predict that for me. Right? So it's sort of like, it's really cool because you're taking machine learning and focusing and turning it on itself. And what I want to do is take the probabilities, feed it into that, and build an attack model that will tell me whether or not each data point was in there. Okay. So once I have that attack model created, this is how the attack actually works. So I have access to your model. I'm going to call it, that's the target model here. And I have data that I want to know whether or not it was in your training set or not. So I can pass each piece of data into your model and observe the output. I take that output, and I know what the true label is, and I can pass that to my attack model over here. And that attack model, if I built it to a high accuracy, will tell me whether or not that specific data point was in your private data set. That's how the attack runs. It's relatively simple to implement and understand. The question becomes, to what extent, how do I measure success in here? Okay. If I run this attack, how do I measure success? So what I'm going to do is I'm going to create a graph. On the bottom x-axis there is going to be the accuracy of that target model. That's the one I'm attacking. So I don't necessarily care if it's the state-of-the-art accuracy. It just has to be relatively reasonable accuracy, so something 70, 80, 90%. Whatever it is, let's just pick that as the baseline. What I really care about is the y-axis. The y-axis is a measure of how private that model is to this attack. And so since this is it's a binary classification, right? For any piece of data, it's either in or it's out, right? So over enough data, that's random guessing would be 50%. If you did this attack enough, on average, you're going to be right half the time. So up at the top is perfect privacy. That's where an adversary can't tell, on average, whether or not a piece of data was in or not. The opposite extreme of that is whether or not an adversary can predict with 100% certainty whether or not an image was in there. And so that's all the way down at the bottom. No privacy whatsoever. Whenever it is about this model, an adversary can guess correctly every time. Okay? So ideally, I want to be more toward the top in the way that I apply this. So I can run, I want to run an experiment, so I create just a standard convolutional neural net. Passing the data that we were looking at before, the images. Do some computations on the output. We're going to do the 10 class label probabilities right there. So I can pass in some data, train up the target model. I can take different data and create these shadow models from it and perform the attack that we saw before, the membership index. And when I do that, I get this data point right there. So it's about, the model itself is about 75% accurate, not too bad. But the attack, when I implement it, it's about 70% accurate. I was hoping it would be up here, more toward perfect privacy. So this is telling me that the model is leaking information about my data set. And I want to find ways to kind of push this data point up more toward perfect privacy to ensure that my data is secure. Now, one sort of some ideas behind how that happens is that third point that I talked about earlier, the third force behind what makes machine learning so successful right now. That comes down to the workhorse of machine learning. It's called stochastic gradient descent algorithm. So it's also called, usually just referred to as SGD. So this algorithm, it looks at your data, and you're trying to create this model, right, which is just a bunch of weights, really. And you want to optimize those weights so that your predictions are the most accurate that they can be. And since it's really just a mathematical function, and what you can use, you can take derivatives of that function. So you can take the gradient here with respect to your weights, and based upon that gradient, update your model parameters along the steepest descent. And then you iterate over and over your training data until you get to that accuracy that you want. Okay. So one common belief out there is that during this process of stochastic gradient descent, there are data points that have a larger gradient than other data points. And because the gradient is larger, you're going to follow that gradient. And that's what's going to get stored within your model, essentially. It's storing information within your model. And you can sort of work your way back to information about those data points with the largest information, the largest gradient. And so the differentially private version of this model, what it does is for each data point in there, it'll calculate the gradient. And then it'll clip it to a certain level, a certain threshold that you enter. Okay, so you say, I want gradients to be this large, no larger. At the same time, after you do that, you add a little bit of noise to make it a little bit more random, just to kind of attempt to remove that influence of certain data points. And that's the gradient that you're going to now update your training process with. Okay. This is a visual of what that looks like. So the top row there is a visual representation of stochastic gradient descent. Those gradients can be any size, and you're just kind of clipping them down here. And adding random directionality to it. Okay. Still going to converge. Okay, when you do that, when you use this technique, using that same model, the same sort of training process, what you can do is you can take snapshots along the training process and perform this attack at that snapshot. And if you do that, up here at 4 epochs of this training, you get a model that is pretty secure against this attack. So perfect privacy up here. Unfortunately, the accuracy of that target model is about 22%. Okay. So it's secure, but not very usable. If you let it train up further and further, you'll notice that the accuracy goes up to about 65%, 66% there. But at the same time, as it's going over your data again and again and again, it's extracting more information about that data out. And so the ability to attack it goes up as well. Ends up being about 60%. So using this technique, I did lose a little bit of accuracy. Went from about 75 to maybe about 70 or so, 65. But at the same time, I gained privacy, because now it's a little bit harder to attack it. Ideally, I'd like to have something that is both accurate and private. And that's sort of the goal. Any questions on that? Okay. So that's a whirlwind. But at the end of the day, the point is that as machine learning and security practitioners, you have to be aware that these machine learning models, since they've been trained up with accuracy as the key measure of success, there's some component there that exposes your data. And these models are leaking that information in ways that we don't fully understand yet. And so when you're building these models, you want to obtain a certain accuracy, but you also, depending on your use case, want to keep in mind that it's going to leak that information. And there's this trade-off there between utility and accuracy. We've also seen how machine learning can sort of be used against itself in sort of interesting ways, and this is just one example of it. We also talked about membership inference attack and how to sort of mitigate against that attack. Sort of a whirlwind introduction into it. Are there any questions or comments or discussion? I think we've got a few minutes, but if not, some of the interns that we have on these projects are here, so ask them the hard ones, the hard questions, they'll be here. Otherwise, us. Thank you for your time. I appreciate it.